And finally we get the expression for the impedance of the components L, R and C as L upon RC. And since we have calculated the impedance of this, so this voltage V2, it can be calculated by multiplying this current I2 and the equivalent impedance Z. But here is a concept involved over here. We know that this full circuit, it constitutes my transistor part, and the current is moving from the transistor to this tank circuit. For the sake of sign conventions, we are taking this I2 towards inward. Why? Because we know that as per the sign conventions of H parameters, all the currents flowing inward are positive. But actually this is the transistor, and from the transistor the current is flowing to this circuit. So V2 will be the impedance multiplied by the current flowing through it, and current flowing through it will be the opposite of I2, that is minus I2. So in accordance with this, my potential V2 across the components parallel combination of L and C will be minus I2 into Z. And after putting the value of Z that we have calculated previously, this will be equal to minus I2 L upon RC. Now further, applying Kirchhoff's law at point Q, the current through HOE will be given by. Okay, so again I come here, this is my HOE and current I2 is flowing through it, and at point Q we are to apply the Kirchhoff's law. So this I2, it will be given by this admittance multiply the potential across it plus this current, which is HFE into IB. So from here we come across this equation that my I2, it will be equal to voltage V2 multiplied by HOE plus HFE into IB. So this is the same equation which is written over here, that my I2 is equal to HOE V2 plus HFE IB. So here we are rearranging the terms. HOE into V2 is equal to I2 minus HFE IB. Further here we put the value of V2, and after putting this value we get I2 HOE, because my V2 is equal to minus I2 LRC. So this value is put over here and all the factors remains unchanged. So then there are two terms with I2, we combine them in a single bracket and we finally get I2 is equal to 1 plus HOE L upon RC is equal to HFE IB. Then further is that if I1 is the current through L, then from the division of current we have. For its explanation, I redraw this circuit, that this is my L part, this is the resistive part, this is my capacitor part, and as given, I2 is the current which is flowing after L and C circuit. I1 is the current which is flowing through L. It means some part of this current IC must be flowing through this collector side. So we can very well see that my I2 is equal to IC plus I1 and IC is equal to I2 minus I1. So from the, that is division of current, what my division of current says, that current passing through capacitor multiplied by its reactive capacitance must be equal to the current passing through this branch, that is the combination of L and R. So this will give me an equation like this, that I2 minus I1 into reactive capacitance equal to current passing through the series combination of R and iota omega L. So from here we open this bracket, I2 into capacitive reactance minus I1 into capacitive reactance, and this is equal to I1 into R plus iota omega L. Now here rearranging the terms, I2 term is kept along this side and I1 is kept along the other side, and then further rearranging that I1 is kept on the one side and this complete term is being divided by this. So I get this, that I1 is equal to 1 by capacitive reactance into IC divided by these whole terms. Here again we will take LCM as iota omega C and then cancel out the iota omega C and iota omega C from here. So we get these terms. Further, this term remains as it is. Here for the iota square I get minus 1 and omega square is equal to 1 by LC. So this total factor gives me minus 1 plus 1. So this minus 1 and plus 1 cancels out and I get a simplified term for I1, which is equal to I2 upon iota omega CR. And in the further step we multiply and divide this full term by omega. So in the numerator we get omega term, in the denominator we get omega square term. Moreover, this iota is moved from denominator to numerator with the addition with by putting a negative sign over here. So this is a very common mathematical way of doing this and you all are aware of this. So and further the value of this omega 1 by omega square is put over here. 1 by omega square is equal to L into C. So cancelling out these terms we get I1 is equal to minus iota omega L upon R into I2. Then the further major step is that the voltage which is developed over here, it is magnetically coupled to I1 and this factor is given by this. So we can say that current I1 which is passing through the inductor L, it induces a voltage iota omega Mi1, where M is the coefficient of mutual inductance between the primary and secondary coils. So from here we get applying Kirchhoff's voltage law to the secondary circuit we get. So now we are to apply the Kirchhoff's law to the secondary circuit. And what is our secondary circuit? It constitutes my this voltage developed across this secondary. It is applied through this resistance to this full circuit. Okay, so this can be written in a very simple way like this, that the total voltage is iota omega Mi1 and the voltage developed due to current IB through the resistances series combination of RB and HIE is equal to RB plus HIE plus the voltage source factor which is equal to HRE plus V2. So from here after rearranging I get IB like this Then in this IB we are to put the value of I1 and value of V2. So IB, after putting the value of my I1 and V2 which we have previously calculated, so I get a term for IB. Now this IB is to be put back into equation 6.5, which is this equation. So after putting this value over here, I come across certain terms, and there are very small steps involved over here. For example, in the first step, I2 and I2 will be cancelled out, and in the further step the value of this omega square will be put. Okay, so after putting the value of this omega square, I will be getting this term, and then LCM of these two terms will be taken. Along this side also LCM is taken, then RC is cancelled out. So we get the value for mutual induction like this. Then separating out the various components, for example RB upon HFE into this whole bracket term, plus this RC into this term upon this term, plus this term into this term. That is all the terms when multiplied we get this expanded form of the above equation. And here again there are the very simple mathematical steps that gives me the mutual induction, that is in terms of all the components of these tank circuit as well as the transistor. So we say that this value of M gives the minimum value of the mutual induction that exists for the oscillation to sustain. That is, if this much mutual induction is there, only then the sustained oscillations will be there, otherwise these oscillations will die down.